Write down next topic. Okay. So as we have completed the temperature point, no, now we will go into the heat. So heat is nothing but it is a form of energy. So the next point of what we are going to talk is heat is given to the system and it is taken from the system. Two things. So if heat is given to the system is nothing but like temperature is increased, which is hotness of the body. Heat is taken from the system in the sense like the temperature is reduced, which is nothing but coldness of a body. Okay. Heat is given to the system, so which is nothing but temperature raised, so it is hotness of a body, and heat is taken from the system. So here it is temperature is reduced, which is coldness of a body. Done. So here like if we talk about the heat, no, heat is directly proportional to the temperature. If temperature raised, heat also like the temperature, I mean the hotness increases. If the temperature reduced, the coldness will be taken place. So on one more thing, like I'll take an object. So in this object, no, there is a 1 liter of water is there, and the second object I'll take, in this 500 ml of water is there, like half of the quantity. If I given the same amount of heat to the object, which one will raise the temperature first? 500. So can I say like heat is directly proportional to the mass of the object? If mass is more, heat also will be increased more. So can I say like here delta Q is directly proportional to mass, and delta Q is directly proportional to change in temperature also. So from these two quantities I can say that delta Q is directly proportional to mass as well as change in temperature also. To remove the proportionality, we are adding a constant called C, specific heat capacity. So this is the formula for the heat, mc delta T or cm delta T. Sometimes they will give in terms of S also, okay, both S or C both are equal only. So what is the SI unit of energy? Joules. So as we are talking about heat, it's a form of energy. So heat SI unit also joules only. Okay. So SI unit is joules. Suppose if they give in terms of calories, okay, then I need to convert everything in terms of SI unit. No, calories is nothing but like is another unit. So but in the question if they mention, then what we should do is 1 calorie is nothing but 4.2 joules approximately. Then 1 joule will be in terms of calories 1 by 4.2 calories. The vice versa of this. So any doubt up to this? Can we go ahead of the next topic? So now the topic is principle of calorimeter. Principle of calorimeter. Okay. So let me take an example here. Two glass tumbler is there, okay, which is of one is hot and one is cold. Like hot water is there and cold water is there. If I bring together, what happens for that? Like heat will get transferred from one body to the other body. Okay, fine. But one more point is, one body will lose the heat and one body will gain the heat, no, to attain the normal temperature. Yes or no? So that is the principle we are talking in principle of calorimeter. So delta Q of hot body will be equals to delta Q of cold body. Like one is losing it and one is gaining it. Okay, that is the principle we are talking here. Two conditions I will take, like delta T, here also delta T, but delta T is nothing but we can say that is change in temperature, no. This is for hot I will take and this is for cold. So hot in the sense like initially the body will be in hot temperature. When I mix, it will become a temperature mixture I will take. In this thing, two temperature, one is cold. When I mix, it becomes T mixture. Okay, hot body is there, cold body is there. If I mix together, mix up like temperature has been mixed together. Like I will attain the equal temperature. Okay. Now if we talk about the equation, no, delta Q of hot will be equals to delta Q of cold. So can I write what is the formula? MC delta. Okay, so T hot minus T mixture will be equals to M for cold, I mean mass of cold and specific heat of cold, and this is T mixture minus T cold. Why I am taking T hot minus T mixture and T mixture minus T cold is, when I talk about the hot body, no, for example let me take 50 degrees Celsius, okay, and if I talk about a cold body, this is 10 degrees Celsius I will take. If I mix together, it becomes 25 degrees Celsius, for example we will consider. Okay, this is hot and this is cold and this is mixture. Can I say that temperature of hot body is greater than the temperature of the mixer? Yes, no? And temperature of the mixture is greater than temperature of cold body? So can I consider T hot minus T mixture and T mixture minus T cold? Getting the point? So this is the formula of the principle of calorimeter. You can take down. The next topic is state change. State change. Okay. So there are three things. One is solid, liquid, gas. So if I want to go from solid to liquid, what is the state? It is a melting point. Okay. So if I take ice, it's a solid, na? If I increase the temperature, it will melt. Yes or no? Like ice cream is there, you will say it has been melted, it become liquid, right now. So first one is melting point, it becomes liquid. So liquid to gas, boiling point, vaporization, right now. So solid to liquid, it's a melting point, it's a melting point. And liquid to gas, it is vaporization, vaporization. Then gas to liquid, condensation, it is condensation. And liquid to solid, it is freezing point. So solid to liquid, melting, liquid to gas, vaporization, gas to liquid, condensation, liquid to solid, freezing, and one more thing is solid to gases, sublimation. So when we are talking about this state changes, till now we were talking about the increasing of the heat of a given body. Okay. Now we will talk about the state changes, like there is no increasing of the temperature but changing of the state. So that is called as latent heat, we will say. Okay, right on the point. Latent heat, latent heat. Keep a hyphen. Heat is used to not raise the temperature, to not raise the temperature. Heat is used to not raise the temperature, but to change from one state to another state, one state to another state, one state to another state. So listen, as we are talking about delta Q is directly proportional to delta T, delta Q is directly proportional to M. So what is this point is telling? This point is telling that it is not about the temperature, it is about the state change. So I will neglect this point now. I can use only this, no? Delta Q is directly proportional to M. So can I say like delta Q is equals to remove the proportionality, we are adding a constant called L, so into M. So this L is nothing but latent heat. Okay, latent heat. So in question they will say that like temperature has been raised, then I can use that formula, delta Q is equals to MC delta T. In the question if they say state has been changed, then I can use this formula, delta Q is equals to L into M. Okay, there is only two state change, one is solid to liquid, liquid to gas, that's it. Okay, you can take this formula. Completed. So L is nothing but coefficient of latent heat. L is nothing but coefficient of latent heat. So the SI unit of latent heat is L is equals to delta Q by M, no? I can write this. So delta Q, it is heat, so joules per kg. So this is my SI unit. Joules per kg is the SI unit of latent heat. The CGS unit is nothing but calories per gram. CGS, MKS unit and CGS unit, centimeter gram second, and MK is nothing but meter kilogram second. MKS is the SI unit and CGS is the other unit. Okay. Under this note point, latent heat of fusion, latent heat of fusion, latent heat of fusion of water, latent heat of fusion of water is equals to 80 calories per gram, 80 calories per gram. Latent heat of fusion of water is 80 calories per gram. The next point is latent heat of vaporization of water. Latent heat of vaporization of water is 540 calories per gram. So try to memorize this. So latent heat of fusion of water is 80 calories per gram. Latent heat of vaporization of water is 540 calories per gram. Sometimes they won't give this data. Okay. So what is the SI unit of the specific heat capacity now? The previous one. MC delta T is equals to delta Q, right? So C will be equals to delta Q by M into delta T. So it is joules per kg Kelvin. Joules per kg Kelvin is the SI unit of specific heat of capacity. Application. Joules per kg Kelvin. Applications. Application number 1. Application number 1. If there is change in temperature, if there is change in temperature, so application number 1 is if there is change in temperature but no change in state. then we should use this formula, delta Q is equals to MC delta T. Application number 2 is, if there is change in state but no change in temperature, then we should use this formula, delta Q is equals to M into L. Application number 3 is, if there is change in temperature as well as change in state, then we should use this formula, delta Q is equals to MC delta T plus M into L. So, only 3 applications. If only temperature change, MC delta T; if only state change, M into L; if both are changing, MC delta T plus M into L. So, what is the first note point? So, if like effect of pressure on boiling point, so if boiling point increases, like pressure increases, boiling point increases; if pressure decreases, boiling point decreases. Okay. Next one is effect of pressure on melting point. So, if pressure increases, melting point decreases; if pressure decreases, melting point increases. So, melting point is inversely proportional to pressure and boiling point is directly proportional to pressure. So, any doubt up to now? Write down next topic. Mode of heat transfer. So under this we are having three types. One is conduction, second one is convection, third one is radiation. So what do you know about this conduction, convection, radiation? Tell. You were telling them something, na? So what is conduction? Only in conduction medium will be there. Conduction, radiation. Radiation, there is no medium. If I talk about sun, is there any medium between me and sun? No. So conduction and convection having medium, and radiation no medium. Okay. And one more point is, in conduction there is no movement of the particle, but in convection the actual movement of the particle will be there. Conduction, only vibration of the particle will be there. Okay. So one particle start vibrating and it will pass to the next particle. So it will keep on changing, okay, from first particle to the infinite particle. Okay. So for example, solid iron rod, if I take, if I increase the temperature of the iron rod from this point, I am not keeping the iron rod at, like total iron rod in the hotness, like only this point I am increasing. What happens? It will transfer the heat slowly to the other end, right? No, so it will transfer, no, like is it a constantly it will transfer, or suddenly it will transfer? It will transfer constantly, right? Now, and what happens here is, if I try to increase the temperature, the particles start vibrating. Okay, vibrating in the sense, like, can I say the kinetic energy? Vibration, no. So it's a motion of a particle only, no vibration. So kinetic energy will takes place. Okay. So once the kinetic energy takes place, no, like it will produce to the other particle, like it keep on change to the other particle, and when the temperature rise to the maximum thing, it will start melt, like expansion takes place, no? Yes or no? Like if I start, like if I produce around 630 something degree Celsius for the aluminum, it will start melt. But if I keep in 500 degree Celsius also for the aluminum, so it won't melt. So there is one I have studied in mechanical engineer. Okay, so no need to worry about those things, they won't ask. Okay. Similarly for iron also. So if iron is equal to the aluminum, so I need to produce more temperature, no? So for example, if we consider the iron rod is melting at 1100 degrees Celsius, if I produce 800 degrees Celsius, will it melt? No. So I need to increase the temperature. Okay. So in this point, what we can understand is, conduction, the flow of heat will be constant. The heat flow, the rate of heat flow, the rate, this one we have discussed in the work energy power also. Rate is nothing but with respect to time. The rate of heat flow is nothing but Q with respect to T. Okay, Q with respect to T. So if I increase the length, then it will take more time to pass the heat to the other end, no? So can I say it is inversely proportional to length? Yes or no? Yes. And Q by T is directly proportional to area also. and Q by T, like if I increase the temperature, the heat also will pass as soon as possible, no? Can I say delta Q by T, I mean Q by T is directly proportional to delta T? If I increase the temperature, if I keep 10 degrees Celsius or if I keep 20 degrees Celsius, which will go fast to the other end? So obviously delta T is directly proportional to Q by T, no? So from these three things, can I say del Q by T is directly proportional to A delta T by L. So Q by T is equals to K A delta T by L. This is the formula for the rate of change of heat. Okay, take down. Under conduction, write down first 3 points: conduction, convection, radiation. Conduction, convection, radiation. So under conduction, the first point, heat is get transferred due to vibration of the particle, of the medium. Okay. So next you can take this diagram. Let me take this as T1 and this as T2. So which is having more temperature? So T1 is greater than T2. So from this formula, no, delta Q by T is equals to, this one I can write in terms of H also. Delta Q by T is nothing but H. So rate of heat transfer is equals to K A T1 minus T2 by L. Okay, completed. So we have learned this series resistance and parallel resistance in class 12th, no? So if series resistance are given, R is equals to R1 plus R2 plus up to Rn. If parallel, 1 by R1, 1 by R1 plus 1 by R2 up to 1 by Rn. Okay. Similarly, we will talk about the series rod and parallel rod here. Okay. So what is current? We were discussing as you have know about the current. Flow of electrons per unit time. So I will be equals to Q by T, no? The charge by T. Yes or no? So I is equals to Q by T. Can I say H is equals to Q by T also here? Both are equal. I can equate them. Okay. Here charge is flowing, here heat is flowing. Per unit time. What is the formula for the current with respect to voltage and resistance? V is equals to, okay, V is equals to IR. What about V by R? So this is delta V I'll take, the potential, change in potential. So change in potential, consider in terms of change in temperature. Current, consider in terms of Q by T, which is nothing but H, and the remaining term is the resistance. So I can rewrite this formula. H is equals to K A delta T by L, H is equals to delta T by L divided by K times A. So, which is similarly looking like I is equals to delta V by R. So, from this R is nothing but L by Ka. If they are asking series rod, then R1 plus R2 is equals to R series. If they are asking parallel, 1 by R parallel will be equals to 1 by R1 plus 1 by R2. Okay. So, try to remember this, or either remember I is equals to delta V by R, convert this. Okay. I will explain once again. So, as we know that current is nothing but rate of flow of charged particle or electron, will say rate, like obviously it is depends upon the time. So, I is equals to Q by T, and we know that V is equals to IR. So, I will be V by R. Okay. Here potential is nothing but from one end to other end we are talking, no. Similarly, we are talking about the temperature from one end to other end. Getting the point now? Potential is nothing but like I am talking from one end of the object to the other end of the object. Similarly, here also we are talking about the temperature from one end of the object to the other end of the object. So, as we got the relation for current, as we got the relation for potential, the remaining term is resistance. So, that remaining term is nothing but L by K times A. Okay, L by K times A. Now, if I talk, this is my parallel. So, in parallel, which is same? Length will be same or area will be same? In parallel, L will be same. Parallel, no? Length is same, no? But in series, area will be same. Okay. Remember two condition, in series area will be same, in parallel length will be same. You can take down. Write it properly, this one. I guess it's not there in the book. It's not there. The next topic is convection. Convection. Huh? Conduction completed. Write on the first point. The heat flow takes place by the actual movement of the particle. Heat flow takes place by the actual movement of the particles of a medium. So in this you need to understand that conduction is for everything, solid, liquid and gas, okay, and convection is for fluids, liquid and gases, okay. Like they might ask question like is which one is for solid and which one is for fluid, like that. So conduction for everything, convection for only fluid, okay. The next point is hot air is less denser and the cold air is more denser. Hot air is less denser and cold air is more denser. Okay, that's it. This about convection. That's it. So next one is radiation. There is nothing more in convection. Next is radiation. First point, heat transfer doesn't require any kind of medium. Heat transfer doesn't require any kind of medium. Example, sun. Heat transfer doesn't require any kind of medium. Example, sun. So if I consider a body, okay, if a light ray is coming and hitting the body, so what happen? It will get reflected, it will get absorbed, it will get transmitted. Three things happens, okay. So Q will be equals to, write down, Q will be equals to absorption plus radiation, absorption plus radiation plus transmission. So R plus T plus A will be equals to 1. The sum of radiation, transmission, absorption will be equals to 1. For example, if one is coming and hitting, it has been splitted into 3 parts. So if I consider these 3 things, it should be equal to 1 only, no? First point, note point. If an object is perfectly transmitter, then T is equals to 1. If T is equals to 1, what is the condition for R and A? R is equals to 0, A is equals to 0. Second point, if there is no radiation, if there is no radiation, if there is no radiation means condition is R is equals to 0, then A plus T will be equals to 1. Third point, if an object is perfectly reflector, if an object is perfectly reflector, R is equals to 1, then A and T will be equals to 0. Next point, if A is equals to 1, it's perfectly absorption. If object is perfectly absorption, A is equals to 1, then T and R will be equals to 0. Okay. So the last point you have written A is equals to 1, no? So which means perfectly absorption. So this is called as black body. This is called as black body, which means a black body absorbs everything. Black body absorbs everything. So from this only, like usually the people tells that don't used to wear this black, okay, in summer. So there is it's a myth, it's a fact, okay, it's a myth, like usually they'll tell that bad things happens kind of thing, okay, it's a myth. So the fact is it will absorb the heat compared to the other colors. Black color will absorb heat more, okay. Completed. Okay, next point, next subheading, emissivity, 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 which is denoted by small letter E. Right on the first point, emissivity is the ratio of emissivity is the ratio of emissive power of emissive power of any body, emissive power of any body to the emissive power of black body, to the emissive power of black body. So emissivity is nothing but ratio of emissive power of any body to the emissive power of black body. Completed. So E will be equals to emissive power of any body by emissive power of black body. So then the next point, emissive power is nothing but E is equals to emissive power capital E, emissive power capital E, E is equals to capital E is equals to, it is the ratio of energy by area into time into wavelength. energy by area into time into wavelength. Done. Next subheading, Wien's displacement, Wien's displacement, W-E-I-N-S, Wien's displacement, W-E-I-N-S, Wien's displacement law, Wien's displacement law. First point, this Wien's displacement law talks about, this Wien's displacement law talks about, this Wien's displacement law talks about wavelength and temperature relation, wavelength and temperature relation. So wavelength is inversely proportional to temperature, wavelength is inversely proportional to temperature. To remove the proportionality, we are adding a constant called B. So B is nothing but Wien's law, coefficient of Wien's law, coefficient of Wien's law, or Wien's coefficient, or Wien's constant, whatever the word we can call that one. Wien's constant also we can say. Next subheading, Stephen's formula, Stephen's formula, Stephen formula, S-T-E-F-F-E-N-S, S-T-E-F-F-A-N-S, Stephen's formula. So in this first point, it talks about emissive power and the temperature. It talks about emissive power and the temperature. So emissive power is directly proportional to T power 4. Emissive power directly proportional to T power 4. Sometimes they have given this E in terms of P also. P is directly proportional to T power 4 or E is directly proportional to T power 4. Okay. So to remove the proportionality, we are adding a constant called sigma. And this E is directly proportional to area also. So sigma A T power 4, sigma A into T power 4. So sigma is nothing but Stephen-Boltzmann's constant, Stephen-Boltzmann constant. A is nothing but Stephen-Boltzmann constant. Okay, completed? I also completed.